Hello everyone, I'm Hao from Tsinghua University. Today, I'll present our work, SingularFS, a billion-scale distributed file system using a single metadata server. This is a joint work with Professor Youyou, Wenhao, Xiaojian, Shaoxun, and Professor Jiwu. I will start with the background and motivation. Billion-scale distributed file systems dominate modern data centers. Here, we call them billion scale as they contain less than billions of files. For cloud service vendors and small-scale clusters, the file number is within billion scale. Some hyperscale clusters, such as Alibaba, also manage their files using billion-scale file systems. At this scale, using a single metadata server is desirable and possible. Compared to using more metadata servers, using one metadata server benefits from easy implementation and TCO reduction. Also, a single metadata server has enough capacity to support billions of files. However, does a single metadata server have enough performance to support billions of files? New hardware provides performance opportunities for metadata. As shown below, new network and storage hardware such as RDMA NIC and persistent memory, has almost an order of magnitude higher small granularity IOPS compared to other solutions. As metadata is typically tiny, this IOPS provides performance opportunities for metadata. However, existing solutions fail to fully utilize the hardware and provide desirable single-server performance. Existing solutions can be divided into two categories: local PM file systems and distributed file systems. The figure below shows their throughput of file create operations in private and shared directories. In private directories, existing file systems show at least 8 times lower throughput than the theoretical value. The performance gap is even more serious in a shared directory. We find 3 challenges that contribute to this performance gap. The first challenge is the crash consistency overhead. Current file systems use write-ahead logging or log structure design to guarantee crash consistency for metadata. However, write-ahead logging causes double write of metadata and in-order checkpoint, while log structure design causes garbage collection overhead. The second challenge is concurrency control in a shared directory. In this figure, there are 3 server threads creating F1 to F3 in A concurrently. However, as they all need to modify A's directory entries and inode, they should acquire A's write lock, which causes high log contention. The third challenge is NUMA scalability. To better exploit the performance of a single metadata server, we need to scale the file system to multiple NUMA nodes. To support this, existing solutions can be mounted to a RAID 0 device spanning across all the PM DIMMs. In this striped layout, the metadata is randomly scattered to different NUMA nodes. This method cannot ensure NUMA locality for create and delete operations. For example, NUMA locality of creating F1 cannot be ensured as its parent directory B and F1 itself are in different NUMA nodes. Next, I'll introduce the design of SingularFS. SingularFS is a billion-scale distributed file system using a single metadata server. This figure shows its architecture, which consists of clients and servers. In SingularFS, we focus on 2 parts of optimizations: metadata storage and metadata operations. For metadata storage, SingularFS uses hybrid inode partition to ensure NUMA locality of file operations. For metadata operations, server threads leverage hierarchical concurrency control to maximize their parallelism and use log-free metadata operations to convert them to non-transactional KV operations. Next, I'll describe the key designs of SingularFS, each of which addresses a challenge mentioned before. First, I'll introduce log-free metadata operations. We classify metadata write operations into 3 categories. Single-node operations, such as open, close, read, and write, only update the target inode. Double-node operations, such as make directory, remove directory, create, and delete, update the target inode and the parent directory. Rename operations, such as directory rename and file rename, update the old inode, new inode, and the 2 parent directories. As rename operations rarely happen, we don't focus on them in this work and use journaling to guarantee their crash consistency. For all the other metadata operations, we transfer them to non-transactional key value operations without additional crash consistency cost, leveraging the dependency between the metadata, the parent metadata and the child metadata. To achieve this goal, we need 2 steps. Step 1 is use kvstore to collocate directory entries and inodes. We use parent ID plus name as the key, use inode itself as the value. Then the directory entries and inodes are collocated in the kvstore. In this directory operation, we need to get all the directory entries of a particular directory. In this figure, we want to get the directory entries of A. To do this, we first use prefix matching with A's ID 1 to get all the KV pairs of A's children, namely B and F1. Then we extract the keys and values to fill in the directory entries, B and F1 for inode name, the inode itself for inode ID and type. After this, the crash consistency of single node operations are naturally guaranteed by the kvstore. Now let's see double node operations. Traditionally, in POSIX semantics, double node operations like file create and delete need to do 3 things atomically. First, create or delete the target inode. Second, update the parent's directory entry. Third, update the directory's ctime and mtime. The reason why we should update mtime is that we modify the directory entries, which is in the data blocks of the directory. The reason why we should update ctime is that in POSIX semantics, the ctime is not the create time but the metadata change time. As mtime in metadata is modified, ctime should be modified as well. These 3 things should be done atomically. After using kvstore, the first 2 steps are merged into one kv operation to update the inode and directory entry at the same time. However, we still need transactions to atomically execute the remaining 2 kv operations. How to eliminate the transactions of these 2 kv operations? We observe that parent inode ctime is not smaller than all the child inodes born time or death time. Based on this metadata dependency, we introduce step 2, ordered metadata update, to eliminate the transaction. We take file create as the example. As shown in the right figure, we create F1 in A at time 5. First, insert the target inode F1 with its born time 5. Second, update the parent's timestamps to the target inode's born time 5. If the system crashes between these 2 steps, as we have recorded the born time of each inode, we just update the parent's timestamps to the maximum of child inode's born time. By doing this, the 2 transactional KV operations in double node operations are transformed into 2 ordered KV operations. They do not have transactional dependency, so they can be executed one by one as non-transactional KV operations. Recall that crash consistency of single node operations is guaranteed with kvstore. So after these 2 steps, we make most of the metadata operations log-free, except for rename. The second design is hierarchical concurrency control. Our goal is to minimize the critical area of double node operations in a shared directory. Traditionally, as these operations need to update the shared parent's directory entries and timestamps, they must be serialized. Using kvstore cannot solve this problem. The transactions have conflicts for the shared parent's KV pair, so they need to be partially serialized. Although log-free metadata operations can eliminate the transaction of the 2 KV operations, the timestamp update operations still need to be serialized, as the conflicts are not eliminated. Leveraging the memory semantics of PM, we replace the second KV operation with the in-place 16-byte atomic operation. So the critical area of operations in a shared directory is minimized. This replacement is based on an observation. Double node operations only update the parent's timestamps, so we treat them specially in the hierarchical concurrency control. We classify the operations related to an inode into 3 categories: updater, writer, and reader. Updaters are the timestamp update operations For example, file create is the updater of the parent directory. Writers are other update operations. For example, file create is the writer of the target inode. Note that file create has 2 different roles for the 2 related inodes. Readers are metadata read operations. For example, file stat is the reader of the target inode. The concurrency control protocol is hierarchically divided into 2 layers. The first layer is read-write lock, which synchronizes writer with other operations. Writers acquire the write lock to guarantee their exclusive access. Updaters and readers acquire the read lock to improve their concurrency. As updaters and readers both use the read lock, we need to further synchronize them using the second layer. Updaters use 16-byte atomic operations to synchronize with each other. To avoid reading the inconsistent value, readers use optimistic concurrency control, or OCC, based on timestamps to synchronize with updaters. Here, we show 2 examples for the second layer of concurrency control to further clarify it. The first is concurrency create in a shared directory. In the figure below, thread 1 create F1 and thread 2 create F2 concurrently. Recall that file create is the writer of the target inode F1 or F2 and the parent directory A's updater. So the thread 1 acquires F1's write lock and A's read lock. Thread 2 acquires F2's write lock and A's read lock. Then the 2 threads insert F1 and F2 KB pairs concurrently. Now the timestamps of A are inconsistent. To fix this, the 2 threads apply 16 bytes atomic compare and swap to A's timestamps. However, in this process, there may be concurrent readers of the parent directory. How to guarantee their consistency? We adopt optimistic concurrency control to readers. However, optimistic concurrency control needs a version number. We observe that inode ctime has the same semantic as a version number. Every time the inode is modified, its ctime monotonically increases. Here is an example of how to synchronize directory stat with other operations. The figure shows the whole process. As the stat is the reader of the target inode A, it acquires A's read lock, then uses ctime as a version number for optimistic concurrency control. It reads the ctime before and after reading the metadata. The acquired metadata is valid if the ctimes are equal. The third design is hybrid inode partition. For single node operations, NUMA locality can be ensured by delegating the requests to the corresponding NUMA nodes. However, for double node file operations, it cannot be ensured as the 2 related inodes may be placed in different NUMA nodes. To solve this, we group the involved metadata into the same NUMA node. As double node operations only modify the parent directory timestamps, we separate them from other directory metadata, which we call access metadata. Here, we separate directory A and directory B's metadata. Then, we place the timestamps and the child files into the same NUMA node to ensure NUMA locality of file operations. As shown in the figure, we place B's timestamps with its subfiles F1 and F2 into NUMA 0, and A's timestamps with its subfiles F3 into NUMA 1. Further, we find that using one tree index inside each NUMA node causes high log contention, which limits metadata performance. We use a simple but efficient method that partitions the intra-NUMA tree into multiple tree indexes. For point query, we directly hash the key to a subindex and get the result. For range scan, we scan all the indexes inside NUMA and combine the results. Next, we show some evaluation results. The evaluation is performed on 1 server and 2 clients. Each machine has 2 NUMA nodes. Metadata is stored in the Intel Optane DIMMs. We compare SingularFS with state-of-the-art file systems, ext4, Nova, InfiniFS, and CephFS. MD-test benchmark is used for metadata performance, and FileBench is used for end-to-end tests. We first report the metadata latency of SingularFS. For SingularFS, InfiniFS, and CephFS, the result includes network latency. For Nova and ext4, it doesn't. As a distributed file system, SingularFS shows comparable latency with local PM file systems Nova and ext4 on file operations. Furthermore, SingularFS shows at least 2 times lower latency than distributed file systems on file create and file delete operations. Therefore, SingularFS shows comparable latency with local PM file systems and lower latency than distributed file systems. For metadata throughput, SingularFS has a higher throughput than local PM file systems. SingularFS shows higher per NUMA throughput than Nova and much higher throughput than ext4. Furthermore, SingularFS has about an order of magnitude higher throughput than distributed file systems. The performance boost is because of log-free metadata operations and hybrid inode partition. Here, we report the throughput of operations in a shared directory. As shown in the figure, SingularFS shows a significantly higher throughput than other file systems in a shared directory, thanks to its hierarchical concurrency control protocol. We prove that SingularFS can efficiently support billion-scale directory tree. We gradually increase the file number of the directory tree until it achieves billion scale, and evaluate the overall throughput. This figure shows that in billion-scale directory tree, SingularFS shows a steady performance and outperforms other file systems by about an order of magnitude. Finally, I will give a brief conclusion. The performance of a single metadata server still needs to be exploited to support billions of files. In this work, we propose SingularFS, a billion-scale distributed file system using a single metadata server. It includes 3 techniques to optimize the metadata performance: log-free metadata operations, hierarchical concurrency control, and hybrid inode partition. Evaluation shows that SingularFS shows comparable latency with local PM file systems and has higher throughput in both private and shared directories. If you want to know more about the design and evaluation, such as the lazy recovery mechanism and the interesting end-to-end benchmark results, please check our paper. That's all. Thank you for listening.